So our next speaker and the last for these sessions in March 2021, 2022 is Pratyush Mishra, who will talk about the dynamics of primitive elements and the group actions.
Thank you so much for the introduction. And again, my apologies for any inconvenience caused. But I have it ready here. So I'll be talking about some dynamics of primitive elements under some group actions. By the way, I'm Pratyush Mishra. I'm a visiting assistant professor in the mathematics department at Wake Forest University in North Carolina. So let me get started. I'll start with some definition of uh, girth for graphs, and then we talk about some groups, and then we go to some group dynamics. So for a given graph, the girth is defined as it's the shortest non-trivial cycle or non-backtracking closed circuits. For instance, for a tree, the girth is defined to be infinite. So there is no zero girth. So the girth is either a finite number or infinite. Um, So here's the tree, the girth is infinite. For a closed graph here, as you can see, the girth is 3 because we have a cycle. For n-gon, the girth is n, and as n approaches infinity, for instance, like the integers, and yeah, the girth is z. So, right. So for a given group, G, finitely generated group, I can talk about, or I can consider the set of all finite non-empty subsets of G that generates G. So I'm considering set of all finite um, subsets, non-empty finite subsets of generators. And then I'm defining the girth of the group with respect to a particular generating set as the long length of the shortest cycle in the Cayley graph. So given a finitely generated group, we can associate a Cayley graph to it on which the group acts isometrically, but there's isometric action on the Cayley graph. And then one can talk about what is the girth of the group in that with respect to a fixed generating set. And then one can define the girth of the group as we take the supremum over all finite set of generators. So a natural question is whether the supremum is finite or infinite. So if the supremum exists, then we say it is finite and the group is of finite girth. If it does not, then we say it is of infinite girth. So here are some groups of finite girth. So Z mod NZ, finite cyclic group, any finite groups. And it's a result of Schlemer that it says that any non-cyclic group that satisfy law has finite girth. So for instance, by law, I mean, if you can find a non-trivial word in the free group with k generators, so such that if I plug in any k elements from the group to the word, then I get the word evaluates to identity. For instance, the any abelian group satisfy the commutator law. So any nilpotent group, let's say upstep K, satisfy, I can obtain a law from upstep K from the nilpotence in C class. Similarly, solvable groups satisfy a law. I can obtain a law from the derived series. And groups of infinite girth is Z. Although Z is abelian, that's just a, I would say, exception. So when I say, and that's the reason I say non-cyclic group satisfying a law. So, right, so Z is just an exception. It has infinite girth. So, right. So any free group, non-abelian free group, meaning by free group, I mean there is no relation in the group. There are just generators and no relation. They have infinite girth. And it's a result of Akhmedov that shows that in SLN-Z, the group of special linear matrices with entries from Z for n greater than equal to 2 has infinite girth. So this is a result of Akhmedov and myself, my advisor, we were able to prove that if A and B are proper isomorphic subgroup of a finitely generated group G, then the girth of the HNN extension of the group has infinite girth, as long as in the HNN extension, the subgroups are proper subgroup. So I need to define what an HNN extension is first. So the idea is essentially, so given a group, if I have two isomorphic subgroups, then one would like to construct a bigger group where the subgroups A and B are not just isomorphic, but they are conjugate. So you literally declare them to be conjugate. So the bigger group is what we call the HNN extension. And we are able to show that as long as the subgroups are proper subgroup, then the girth is always infinite. So the key construction in the proof is just some use of Britton's lemma. So that's something one used to decide when a word is non-trivial in the HNN extension. And then there is a clever way of the first step is cleverly separating or yeah, getting a generating set which is disjoint from A and B. And then this Britton's lemma, yeah, we use that to somehow play a ping pong dynamics in the sense that, um, and that somehow guarantees the infinite growth. So by ping pong, I mean, so there is this classical um, lemma in geometric group theory that says, let's say in most elementary version, it states that, let's say I have a non-empty set X, and if I consider the group of bijections of the set X, and if I take F and G to be two such bijections, and if I can find two non-empty disjoint subsets A and B in the set X, such that any non-integer power of F maps A to B, and any non-integer power of G maps B to A. So if I have this ping pong, then this F and G generate non-abelian free group. So that's basically a classical way of generating free group, historically speaking, and that has many different ways or versions that appears. And it turns out that for certain classes of group, this property of having infinite girth coincide with this property of producing this ping pong in some strong sense. And yeah, we prove infinite girth from there. So, right. I'm not able to go back and forth. Okay. Yeah. So, right. So then we were able to extend this result to any HNN extension of non-elementary word hyperbolic group. And yeah, the idea is again, basically, it's not similar to the previous one, of course. There is a Britton's lemma. It's a completely different idea. Here, we consider the action of the group on the Gromov boundary and the dynamics of the ping pong pairs of the loxodromic element that you find in the boundary, where the boundary actions, and then, yeah, use that to guarantee the infinite girth. So, so I'll just take a little bit algebraic digression now to define few other notions before coming to a few more like yeah, group actions, the result as per my topic of the talk. So the Schreier-Girth. So we have these Schreier transformations. So we talked about girth of a group with respect to a fixed generating set, right? So it is possible that the girth of the group with respect to a generating set S is infinite, but let's say there might be another generating set S prime that we can obtain from S by a finite number of Schreier transformation, and the girth of the group with respect to S prime is finite. So by Schreier transformations, I mean um, transformations that or the generating set that we obtained by these three moves. So you by switching the generating set, or by replacing Si by Si inverse, or any Si by SISJ. So they does not really change the generating set. It is still the same generating. I mean, as a group, it still generates the same, but the generating set changes. So the question is, yeah, so that's basically the motivation. So you start with a group of infinite girth. Can we wiggle somehow our generating set to a different generating set to obtain a group with finite girth with respect to the S prime? And that motivates further to this definition of primitive elements. I think uh, rather than going through this long definition, it's better to understand this by an example. So an element X is primitive if, let's say, I can find a generating set in my group such that, and I can replace this element X by some element in the generating set of S, and it is still a generating set. So then we say the element X is primitive. Primitive. That's basically and this is more rigorous way of defining it. And then we talk about what is the first step primitive element and the second step primitive element. So basically, yeah, historically, even these are important objects in group theory. People study it for many group theoretic reasons, I would say. But we use a dynamical approach and study some conjectures and obtain some preliminary results in some directions, which I'll show in next couple of minutes. So let's say this free group. Let's try to understand this with the free group example with two generating set X and Y. This is the first step primitive element. So meaning, right. So first step means I can replace this any element in this first step primitive element by the standard generating set X comma Y, and then it is still going to be a generating set. For instance, Y. I can replace Y in the generating set X comma Y by X to the power ny, right? And then X comma X to the power ny is still a generating set that generate F2 because I can use this X to kill all this X to the power n in the group. So that's the first step primitive element. Similarly, this is the second step primitive element, and I obtained this inductively, I mean, from the first step. So I can, yeah, so I obtained this from the first step. So, and then one can talk about third step primitive element, fourth step primitive element, and so on. Yeah, here is just an example. So it turns out that an example, yeah, which is an element which is not primitive is, let's say, x square. Just x square is not primitive or y square is not primitive. Right? So I cannot replace x square by x, and it is not going to be the same generating set. It is going to be a proper subgroup. X square comma y is a proper subgroup. It's not the whole group, right? Similarly, the commutator is not a primitive element. So a motivating example of this business of primitive element, which I'm talking about, came from this paper of Platonov at Potapchik. So a square matrix X is unipotent if for some integer n, a minus I raised to power n is zero, right? Or the zero matrix. So Platonov Potapchik came up with this 4 cross 4 matrix X and Y, and they noticed that X to the power ny is unipotent. However, yxy is not unipotent. So, and also this, if we consider this group generated by x comma y, this set of these elements, x to the power ny, these are like all that looks like this first step primitive elements, right? So they are all unipotent, but the whole group is not unipotent. So here, this is basically the conjecture. So for a general linear group G with a fixed finite generating set, if all the primitive elements are unipotent, can we say the group G is necessarily unipotent? So this is a big open conjecture, and then they proved it for um, certain cases for the free group under some strong assumption on the Jordan block, size of the Jordan block. So for any non-abelian free group Fn, if I consider this automorphism from, I have a finite dimensional representation of odd Fn in GL and C, and assume that all the images phi of x, where x is primitive, are unipotent, and the number of Jordan blocks does not exceed n, then the images of phi of the inner of Fn or inner automorphism of Fn is unipotent. So, right. So we basically rephrased this conjecture for group actions, to be more precise, and then we studied it for certain group actions. So for instance, let's start with this group G with this fixed generating set S, and then G act on some manifold X, and then one can ask this question: if P acts freely on X without any fixed point, then is it true that the whole group act freely? So these are very broad questions. Now, if fix of S is non-empty for all S in the first step primitive element, meaning all the first step primitive element fixes something, then is it true that the fix of G is non-empty for all G in G? So this need not be a global fixed point, but for any particular G, the fixed point set is non-empty. And then what if we replace P by P1 or the first step primitive element? So yeah. So sorry. So P means set of all the primitive elements, and P1 means the first step primitive elements. Okay. And then one can also ask like, what if we replace P1 by P2, or what if we replace P2 by P3? So we were able to obtain certain results. It seems like, and it turns out that one can make, it actually turns out that this is the right way of phrasing this conjecture for group actions, at least in this three. To be more precise, it is question two actually. Um, and then it makes sense to study these questions. So yeah, so these are some of the results that we obtained for the affine group action of R on the real line. We prove that this is positive. For SL2 R action on the hyperbolic plane, we prove that it is impossible to answer these questions. It basically, yeah, the question collapses, yeah, based on the group action. For PLI, so meaning the group of piecewise linear homeomorphisms of interval 0, 1, again, the question 3 is negative. We gave a counterexample. And for GL2R action RP1, the projective line, again, question 3 is negative. And we believe there do exist example of non-trivial group actions answering positively question number 2. And that's an ongoing work. We haven't gotten an example so far. So yeah, this is the PLI, the third one, the counterexample. So where all the first step primitive element, so this F is a piecewise linear map from the interval 0, 1 to 0, 1, and G is a piecewise linear map. So one can, yeah, so we proved that basically, yeah, all the first step primitive element act freely, but not the whole group act freely. And that proof is essentially, it uses, yeah, some broader idea of intermediate value theorem from calculus 1. And for GL2R action on RP1, this was completely computational. We used Mathematica to come up with this small matrices. And then, yeah, they do the job. So even here, the first step primitive element fixes something, but not the group generated by these two elements. In fact, the counterexample pops up from the commutator actually. And yeah, similar construction can also be arranged in GL n+1R action on RPN. But in the paper, we just did it for the basic base case. Even this was very tricky to find out, but yeah, it is also possible to find for higher dimensions. So we also proved that there exists a subgroup in the homeo I, the group of homeomorphisms of interval 0, 1, such that all the primitive elements of gamma acts freely, but the entire group does not act freely. So in homeo I. So we studied this basically for, as I said, these questions or this reformulation of this conjecture for different class of groups. And then, yeah, I talked about Schreier-Girth, and then let me just define the Nelson-Girth. So in the Nelson-Girth, one thing is we don't switch elements. So if you look at the Schreier-Girth definition, let me go back. So we have these three things, right? So the first one is not there in the Nelson-Girth definition. So right. So either I replace SK by sorry, I'm just Schreier moves basically. So I start with the generating set. So these are just the two steps that I'm allowed to do to obtain a new generating set, right? So these are called the Nelson moves. And then with this, one can define a Nelson girth. Basically, yeah, this is the definition. You take the supremum of girth of the Cayley graph of S prime, and then you take infimum of some fixed size K. And then that's the Nelson girth of step K. And then we are able to basically, yeah, these are some immediate corollaries. And then I don't want to spend more time here, of course, because of the technicalities, but I'll be happy to answer any question. But this was the main counterexample or striking counterexample that we came up in the paper, that we came up with this class of group that has finite N2 girth, but the girth of this whole group is infinite. Now, one may ask that where does this relate to what we have been doing about this group action thing? It turns out that the tools that we use is similar in obtaining such group theoretic result as well. So yeah, so maybe I'll just stop here.
Well, thank you very much. Thank the
Thank you.
speaker.